Hi, my name is Cannon Reeves.
And I'm Kiefer Christ.
And I'm Catherine Rommel, and we're here representing the University of Arkansas NASA Razorbotz robotics team. We decided to break our team down into 5 different subsections, each focused on a different area of the robot. We have our chassis team focused on building the chassis, led by Kiefer. We have the excavation team, led by Mishek, which was focused on building the excavation system. We have the wheels team, led by me, which was focused on making sure that we had the best wheels we could get. And we had computer science, which was focused on the controls of the system and making sure that we had the best control that we could of each component. And we have the electrical system, which was led by Jocelyn, that was focused on making sure we were able to actually run the entire robot. We wanted to build this robot with safety in mind. We wanted to implement a safety plan that had a series of components. The first we wanted to implement was a safe zone around the robot when it was functioning to make sure no one was hurt by an unexpected motion. We also wanted to implement a software stop that made sure we were able to control when the robot moved and when it didn't, and didn't have any unexpected motion due to controls or bumping the joystick, which is what we use to control the robot. We also wanted to implement an emergency stop. This was to make sure that if there were anyone around the robot within the safe zone, we could turn the robot off and we would be safe and make sure that no motion would happen, whether we used the controls or had unexpected motion due to electrical connections. These safety features were implemented using the trigger button on the joystick as a dead man switch. Unless that trigger is held down, the robot will not respond to any software signals. None will actually be sent. The emergency stop was installed on top of the electrical boxes to make sure that we were able to cut power from the batteries to all of the motion systems, though the computer run on a separate system was able to continue operating. And we also developed a safety stand to make sure that when we were testing the robot and iterating designs, we didn't accidentally drive off the table.
All right, so we set out this year with one overarching goal, and that is to improve upon last year's efforts. This is realized into 3 sub-goals, the first of which is to increase our scoring potential. Last year we were not able to reach the minimum 1 kilogram of gravel in a run, and so we wanted to change that. We also set out to reduce weight, because saving weight is the only way to score points before we even step foot in the arena. And we also wanted to increase mining points as a whole. Our philosophy that overarched every decision we made throughout the entire year was to save weight and iterate. Last year's it was to iterate, and that resulted in a robot that functioned better than we ever had before, but it was very heavy. And so by combining the two, we wanted to maintain our philosophy of rapid iteration while still reducing weight and increasing mining points. We set out at the beginning of the year to decide between 2 approaches. The first of which that we used last year was to do a large number of small loads, and the other was to do 1 large load in the entire round. And the benefit of doing multiple small loads is that if it messes up at any one point, you've got some other loads that are redundant. You can also have a simpler and lighter robot. On the other side of that, if you do 1 large load, you are putting it all in relying on one thing, all your eggs in one basket. But on the other hand of that, you have more time for digging and actually excavating. And we also had failure points last year when traversing, and so we thought the less times we're crossing back and forth in the field, the better, and ultimately ended up deciding to do 1 large load and a single trip. When selecting components on this robot, we had a very simple checklist. It started with, is this lightweight? We're not going to put a lot of steel on this robot because it's not very lightweight. And so everything from the material to the size and the geometry of the components we're creating took into consideration the weight. Past that, we looked at can we manufacture it. We are aware of our manufacturing capabilities as well as our sponsors, and we wanted to make sure we could make things that are actually feasible. And we also looked at reliability. Last year we had a robot fail in our second match, and we wanted to prevent that. We wanted a robot that will work consistently. And so that took heavy consideration in the material and the design of components. When deciding a component, we started with a discussion among the team. We moved then to a low fidelity prototype. using either cardboard or 3D printed parts, and eventually had a discussion and made a decision as a team, informed by the prototype. We try to be as objective as possible in these decisions. And with that, I'd like to introduce Bender 3.0, and Kiefer will then now do the demo.
All right, so for our control system, we're using a joystick. I'm gonna go ahead and twist the E-stop, activating the robot. So upon entering the arena, the first thing that this robot has that's very beneficial is the ability to turn on a dime. It can turn exactly where it is in its current position, allowing it to very quickly and effectively orient itself towards the excavation zone. The next step of that, of course, is traveling across the obstacle course. This chassis is designed such that we can drive straight over any crater. Having 3 wheels on the ground is just fine for this robot. We can tank right over that. However, it is not capable of driving over boulders, so we will strive to avoid those upon traversing the obstacle course. Once we get to the excavation zone, we will have the drum hit the ground first, which I will demo now. So the purpose of this drum is to clear away the top layer of sand to allow us to get down deep quickly and effectively. So we would do that for a little while to allow us to clear a giant pocket into the ground, which would then allow for our scoop to fit into that hole. So in order for us to get our scoop down into the ground, we have to lift the arm up, giving us clearance to then switch over to the scoop. Just like so. At this point, we will then drive it down into the ground like a traditional excavator and collect gravel. Just like so, at which point we would then bring that gravel back up, and then we would dump it into the internal chamber of the bin, which allows us to collect more gravel than we could prior. Once it's delivered to the internal dumping bin, we then orient the arm and get it ready for traversing back across the obstacle course back to the dumping zone. So once we travel across and get ourselves lined up the trough, again using our ability to turn quickly and effectively to line ourselves up to where the rear is facing the trough, at which point we would then lift the dumping bin up and over such that it would dump into the trough. At this point, I'm going to go ahead and turn the robot off. So going into our performance goals, one of our main performance goals this year, as priorly mentioned, was to reduce weight. We did this through a lot of different methods. It was crucial to our design choices, and we ended up saving around 37% of our weight over last year. And the reason we put a giant emphasis on this is because it is the only way that we can score points before we actually get our robot into the arena. So another way that we can improve this robot was through the internal bin, allowing us to store more gravel internal to the robot, and then traversing all at once in one load, as again was priorly mentioned. And then our third performance goal was to make sure we maintain modularity. And we did that quite well through the electrical boxes, allowing us to quickly swap out components as our designs change throughout the year. The chassis as well, being designed on 2 tubes, allows us to quickly slide the wheels, our wheelbase to adapt that, and allows the team to maintain flexibility going into future years and possible rule changes.
Alright, so let's talk about where we innovated to create this robot. To start, let's go 3 years back to 2017. This is when Bender 1.0 was born. It was at this time that the team oriented around a drum design. We saw the benefit in a simple mechanism that could both excavate, store, and deposit. What we found with Bender 1.0 was not much because we weren't able to actually make it work due to several failures. But we saw that it was very good at collecting a lot of dirt, but it was also really heavy. So the next year, the focus was transitioned from regolith to gravel, and we created Bender 2.0. We wanted to make a robot that performed in competition and that could effectively score. So we focused on making Bender as simple and iterable as possible. We achieved this by using T-slot for the frame and 3D printed parts all over. One unique thing that Bender had was on its drum were several teeth that faced backwards. So when we spun the drum backwards, we could actually move away the regolith, exposing the gravel underneath, allowing us to quicker excavate it. The issue we ran into was that the drum was not as effective as we had hoped at excavating gravel. So we surveyed other teams, we looked at the components of this design that we liked, and we came to the conclusion that a scoop was the best way to collect gravel, and a rotating drum was the best way to remove regolith. We decided to combine these two in a simple design. Among all of these robots is a 2 degree of freedom arm. We maintained that. All we did was add one more actuator on that. So now the arm is actually counterbalanced and the elbow can rotate infinitely, essentially. To bring this to life, we had to also save weight in a lot of other areas. So the ways that we save weight include the wheels. The wheels are almost entirely 3D printed and use a very lightweight truss design. On the chassis, we used aluminum tubes that were a set distance apart. This means that all of our parts that are on the chassis can actually be loosened and moved along. We really like this and it helped us iterate very quickly. The excavation, it's a lot less modular, but it's also a lot more purpose-built. So we use 2 actuators as opposed to 1 for moving it up and down. We've got a lot of power behind this. We also use 2 actuators on the elbow, and we have encoders that are telling us this elbow position. We also used a brushless hub motor on the drum portion of it. We did this for the sake of throwing a lot of power at it in a very tight and compact and simple design, and it works pretty effectively. The teeth on the drum are also oriented and angled. This allows us to push the regolith away as we're moving. On the controls and electrical side, our whole design system is much more modular. Our boxes are really, really clean and makes it easy to add things around it. We also moved away from using a Raspberry Pi to a Jetson TX2. We did not achieve autonomy this year, but we've developed this robot as a software development platform for next year to make it autonomous. On the software side of things, to further prepare for that, we moved away from using Python to using ROS, all on the robot.
The project management scheme that we adopted was based on Agile project management. We did this because we recognized that each member of our team would actually have conflicts with schedule availability, and we may also run into some issues with design. We wanted to make sure that we were flexible and able to respond to all of these problems. This allowed us to focus on the main parts of project management: the budget, the schedule, and scope. Budget was taken care of by tracking our expenses and also making sure that each item we purchased was versatile and able to be used in multiple different parts of the robot so that we wouldn't have to buy a bunch of different parts. We maintained our schedule by having weekly stand-up meetings, which established not only the progress that had been made the previous week, but also what we plan to do in the coming week. We also had workday meetings on the weekends to make sure that we were able to accomplish these tasks and maintain forward progress. We established 2 main risks that we recognized needed to be mitigated to successfully complete the project. The first risk dealt with clearly communicating with each other, whether we had any issues with schedules or completing tasks. This was mitigated by weekly emails that kept everyone up to date, usually reflecting what had happened in the stand-up meeting and progress that had been made or was planned for the upcoming weekend meeting. And it also helped coordinate activities so everyone was aware whether they were able to attend the stand-up meetings or not. The next risk that we recognized was coming to the end of our schedule and having a robot that didn't function or a part of it that didn't function. To mitigate this, we focused on iterating and actually testing all of our designs early and frequently to make sure that what actually was added to the robot would function and do the job that we needed it to do. Overall, we've successfully completed a robot we're very, very proud of.